You know that feeling when you're working inside a web dashboard and you need to process just this really heavy data set?
Oh, yeah. The spinning wheel of death.
Right, exactly.
Right.
Let's say it's like a 500 megabyte CSV file full of raw sales data or server logs or whatever. You click open and instantly the entire application just completely locks up. The screen freezes. You try to click another tab, nothing happens. You try to scroll and the page is just totally unresponsive.
It's the worst. You're just sitting there.
Yeah. Sitting there staring at a dead window until your OS finally throws up that little, page unresponsive dialog box.
Yep.
And you just have to force quit the browser and you silently vow to never, ever use that tool again.
It is a universally frustrating experience for everybody. And the instinct is almost always to blame your own hardware.
Right.
Or you just assume the application is poorly optimized.
Right. You think, oh, my laptop just isn't powerful enough for this.
Exactly. We assume the computer just kind of gave up under the weight of the data.
Yeah. But the reason that happens actually has nothing to do with your laptop being underpowered.
No, not at all.
So we're taking a deep dive today into this really fascinating article by Aaron Rose. It's from tech-reader.blog, and it's titled Streams API, How the Browser Handles Massive Data Without Freezing the UI.
She was a great piece.
Huh.
Really eye-opening.
It really is. And our mission today is to explore how modern web browsers have kind of secretly evolved to handle massive scale data without crashing. And how this completely changes the mental model we should have for web applications.
Yeah, because the problem really stems from a very traditional, I'd say, synchronous way that developers handle file inputs.
Okay, what do you mean by synchronous in this context?
Well, when you select that massive 500 megabyte file, the standard default command a developer might use is something like await file.txt.
Which sounds completely normal.
It looks totally innocuous, but under the hood, that command is trying to allocate the entire file into the browser's active memory in just one single massive gulp.
Okay, let's unpack this, because to an audience that's familiar with web tech, it sounds like just a simple memory issue, but it's actually an architecture issue.
Right, exactly.
Because a 500 megabyte CSV file isn't just 500 megabytes once it actually gets into JavaScript.
No, it blows up.
Right, because of how the V8 engine encodes strings. It often uses UTF-16, I think, so that memory footprint can easily double.
Easily.
So suddenly, you are trying to shove a full gigabyte of string data into the memory heap literally all at once.
And that massive allocation spike, that's what triggers the browser's garbage collector to go into just absolute overdrive. It recognizes this huge sudden demand for memory, and it basically halts everything else to try and free up space.
It panics.
It totally panics. And because JavaScript execution, DOM updates, and UI rendering all share the exact same made event loop.
A blocked event loop means a frozen screen.
Exactly. The browser physically cannot paint the next frame or, register your mouse click because it is practically choking on the data allocation.
So relying on await file.txt is basically like, well, it's like trying to swallow a whole watermelon in one bite.
That's a great way to put it.
You're going to choke. Or, in the browser's case, trigger a massive garbage collection pause and just crash the tab entirely.
Yep.
But Aaron Rose's article highlights the actual solution to this, which is the Streams API.
Right.
And if the old way is swallowing the watermelon whole, using the Streams API is, it's like putting that exact same watermelon through a juicer and drinking it glass by glass.
I love that.
Right, because you still process the entire piece of fruit, but you do it in these continuous, manageable increments that your system can actually handle.
Yeah, that analogy translates perfectly to the mechanics of what developers call real throughput.
Okay, break that down for us. What is the Streams API actually doing under the hood?
So the Streams API is a set of primitives built directly into the browser's platform. Specifically, you have the readable stream, the transform stream, and the writable stream.
Got it.
So instead of pulling the entire gigabyte of encoded text into the heap at once,
Yeah.
you use a readable stream to essentially siphon the data off the disk incrementally.
Just sipping it.
Right. Maybe just like 64 kilobytes at a time.
Okay, and then you pass those small chunks through a transform stream, right? Which is where you'd apply your business logic.
Exactly.
Like filtering data or reformatting dates, things like that. And then you finally push it out through a writable stream.
Spot on.
Yeah.
And because you are only ever holding a tiny fraction of a megabyte in memory at any given millisecond.
The event loop never gets blocked.
Exactly. It remains completely unblocked.
Yeah.
The garbage collector can effortlessly clean up those small chunks as they pass through.
Whoa.
So your memory usage basically flatlines at just a few megabytes.
That's incredible.
The UI stays snappy, CSS animations keep running seamlessly, and the user actually sees a real-time progress bar instead of just a frozen screen.
Okay, but if I'm mapping this out mentally, I've got data flowing in from the hard drive. It's getting processed by the CPU, and maybe it's being written out to another file. But those three operations, they do not happen at the same speed.
Very true.
Right. So if my local disk reads the file way faster than my JavaScript logic can actually parse and filter it, doesn't the system just flood?
You'd think so, yeah.
Like going back to the juicer, if the juicer is running faster than I can drink, I end up with the juice overflowing all over the counter, which essentially means we just run out of memory anyway, right?
And this brings us to the secret weapon of the Streams API. It's a mechanical feature that, honestly, a lot of high-level overviews just skip entirely.
Okay.
It's called back pressure.
Back pressure. Okay, so how does back pressure actually stop the overflow?
Think of it like an automated factory conveyor belt with built-in sensors.
Okay, I can picture that.
In a stream pipeline, flow control is a native feature. The system is constantly monitoring the internal queues of each individual stream.
Oh, really?
Yeah. Every stream has what's called a high water mark. It's basically a predefined limit of how many chunks it can hold in its buffer at once.
Right, so it has a capacity limit.
Exactly. So if you're processing logic, the transform stream starts falling behind, its buffer fills up, and it hits that high water mark.
And it sends a signal back down the conveyor belt.
Exactly. And the signaling is completely automatic. The desired size property of the stream drops to 0.
Oh, wow.
And the readable stream at the source automatically pauses its pull from the disk. It just waits.
That's so smart.
Yeah.
Yeah.
And once the transform stream chews through its backlog, the signal turns green again, and the source just resumes reading.
Wait, so the developer doesn't have to write any complex, error-prone state machines to manage this traffic jam?
0.
The browser just instinctively coordinates the flow,
Yeah.
braking and accelerating based on wherever the bottleneck is in the pipeline.
Yep, you literally don't have to write a single line of flow control logic. The internal plumbing of the browser handles the back pressure entirely.
That is why.
It perfectly balances the ingestion, processing, and output speeds, which is why, a well-written stream can process a 5 gigabyte data set with the exact same minimal memory footprint as a 50 megabyte data set.
That drastically alters what we should expect from a web application.
Oh, completely.
Because for the last, 2 decades, the overriding rule of web development has been that heavy compute tasks just do not belong in the browser.
Right. Never do heavy lifting on the client.
Exactly. If you have a massive data set, you have to ship it off to a server.
What's fascinating here is how deeply ingrained that mental model really is. Aaron Rose refers to it in the article as the back-end assumption.
The back-end assumption.
Yeah. We've been conditioned to view the web browser as just a thin client.
Like a dumb terminal.
Exactly. Essentially, a highly interactive remote control for a heavy server located thousands of miles away in some AWS data center.
Right.
So if a user needed to filter and format a massive log file, the default architecture was always, build a Python or Node backend. Force the user to upload the file.
Crunch the numbers in the cloud.
Crunch the numbers on your cloud instance, and then eventually give the user a download link when it's finally finished.
Which, when you critically examine that round trip, is just an incredibly inefficient way to process data that is already sitting right there on the user's hard drive.
It's so wasteful.
Let's just look at the friction involved. First, you are blocked by network bandwidth. Uploading a 500 megabyte file over a standard home Wi-Fi connection takes time.
It can take a long time.
Right. And you're dealing with TLS overhead, HTTP serialization, and just the sheer physical latency of routing data across the country.
And this raises a really important question about the privacy implications of that model as well.
Oh, absolutely.
Because the moment you require a user to upload their data set to a server, you are pulling potentially very sensitive data like financial ledgers, internal server logs, personal health information out of their secure local environment.
And moving it across the open internet.
Right, into a third-party server.
Yeah.
From a compliance and security standpoint, the surface area for potential breach just expands massively.
Not to mention the financial cost to the developer.
Oh, the AWS bills.
Right. If you have 100 users uploading gigabytes of data every single hour, you are paying a fortune for cloud compute, server memory, and bandwidth egress fees, just to do basic data transformation.
Which is exactly why the shift to what the article calls the local front-end approach is so disruptive. By leveraging the stream's ATI, the browser reads the data locally, processes it locally, and saves the result locally.
It just cuts the server out completely.
It eliminates the network completely. It functions entirely offline if you want it to.
Right.
The privacy is absolute because the data literally never leaves the user's machine.
And the infrastructure cost drops to literally zero.
$0.
Okay, I want to trace a piece of data through this new local pipeline just to see how it actually works in practice. Because the article breaks down this full end-to-end trip for taking a raw CSV file and turning it into a generated report without ever touching a backend.
It's a great workflow.
So let's visualize this data lifecycle. The user is sitting at their dashboard. They click a button to select a file. But instead of just grabbing a copy to upload, the browser uses the File System Access API.
Right. And the File System Access API is the crucial first step here.
Okay.
It allows the web application to request a file handle, which is a direct reference to the actual physical file sitting on the user's operating system.
Okay, I have to pause you there because letting a web application reach directly into my hard drive to read and write files sounds like a complete security nightmare.
I know, it sounds terrifying at first.
Right. If a random website can just silently edit my local documents or read my private folders, that breaks the entire sandbox model that makes the web safe to use in the first place.
That is a very valid concern, and it's exactly why the API is designed around extremely explicit user-granted capabilities.
Okay, so it's locked down. Very locked down. The browser doesn't just get blanket access to your file system. It requires an intentional user, gesture-like, physically clicking an open file button to invoke the OS's native file picker.
So the browser only ever gets access to the specific isolated file that I manually hand over to it?
Correct. And even then, before the web app can write any changes back to your disk, the browser throws up a very clear, persistent permission prompt.
Okay, that makes sense.
So it is heavily sandboxed. But once that permission is granted, the app has this direct, secure pipeline to the data.
So the moment you grant that file access, the browser essentially establishes a siphon. It opens a readable stream and just starts pulling the data in.
Yep. And as those first few megabytes get siphoned in, they immediately hit the transform stream, which is where your parsing logic lives.
Right.
But parsing a stream introduces a pretty unique challenge here.
How so?
Well, you aren't looking at the whole document, right? You are looking at arbitrary 64 kilobyte chunks of text just rushing past. Right. And this is where it gets really tricky, because a random chunk boundary might slice a row of data right in half. It might cut off right in the middle of a string, or even worse, split a multi-byte Unicode character directly down the middle.
Which will totally break your parser, which is why your transform stream needs to manage a small amount of internal state.
Oh, I see.
It reads the incoming chunk, it processes all the complete lines of data, and then it just holds on to that final dangling fragment of text in its buffer.
Ah, so it just hangs onto the broken piece.
Exactly. And when the next chunk arrives from the disk, it prepends that saved fragment to the new data, creating a complete line, and just continues processing.
That's brilliant.
It's stitching the data together continuously on the fly.
And as it identifies those complete rows, it applies the business logic. It filters out the invalid rows, aggregates the totals, reformats the dates, whatever it needs to do. And because this is all happening asynchronously in these small, highly efficient batches, the main event loop is completely free.
Yep.
The application can calculate the processing speed, update a progress bar in the DOM, and keep the user interface totally responsive the entire time.
And then, as the transformed data leaves that processing phase, it flows directly into a writable stream.
Which goes back to the disk.
Exactly. This stream is connected to another file handle, allowing it to write the generated report sequentially back out to the user's hard drive as a brand new file.
Here's where it gets really interesting.
Yeah.
During that entire life cycle, from the user selecting the initial file, to the parsing logic stitching the chunks together, to the final report being saved, that massive 500 megabyte CSV never actually lived in the computer's memory, not once.
Right.
The stream just fed chunks into a transform, updated the UI progressively, and spit out the result.
It fundamentally redefines the browser's capabilities. I mean, Aaron Rose synthesizes this new architecture by outlining what he calls the 3 pillars of local dashboards.
Okay, what are the 3 pillars?
To build these back-end free data tools, developers are basically orchestrating 3 distinct web APIs. First, the File System Access API, which we just discussed. That provides the secure bridge to the local operating system.
Right. The second pillar is IndexedDB. And this isn't just about storing generic user settings like dark mode preferences, right?
No, not at all.
In this specific architecture, IndexedDB solves a very frustrating user experience problem. Because if a user grants access to a local file, you really don't want them to have to manually click through the file picker every single time they refresh the page or, restart the browser.
Right, that would be incredibly annoying. And the mechanism there is incredibly clever.
Yeah.
Because you can't store the raw file in IndexedDB that defeats the whole purpose of memory management.
Obviously.
But you can store the file system file handle object itself.
Oh.
By serializing that secure reference into IndexedDB, the web app can instantly reestablish the connection to the physical file the next time the user opens the dashboard.
It maintains persistent access. So the File System Access API gives you the raw materials, IndexedDB preserves the connection state across sessions, and the Streams API provides the high-throughput, memory-safe conveyor belt that moves the data through the logic.
Right. And if we connect this to the bigger picture, orchestrating these three APIs literally turns the browser into a local data warehouse.
A local data warehouse. That's a great phrase.
Developers can build highly complex data applications now. Log analyzers, video transcoders, ETL pipelines, and they execute with the raw speed and zero latency of a native desktop application.
But they're distributed with the frictionless accessibility of just, sharing a single URL.
Exactly.
It is incredible to trace the evolution of this technology. We started this deep dive looking at a complete failure of the user experience, a frozen, totally unresponsive browser tab caused by trying to forcefully cram a gigabyte of string data into the V8 memory heap. And by simply adopting the correct architectural primitive, by shifting to the Streams API, we don't just solve the freezing problem, we accidentally unlock an entirely new paradigm.
A total paradigm shift.
We eliminate the need for costly cloud infrastructure. We guarantee absolute data privacy by keeping the payload on the local machine. And we allow massive data processing to happen flawlessly on an airplane without a Wi-Fi connection.
That's revolutionary.
So what does this all mean? Well, for developers, it means the platform has officially matured. The tools are already native to the browser to build applications that deeply respect the user's hardware constraints and their data sovereignty.
You no longer need a massive AWS budget to build a powerful data tool.
Exactly. And for you, the user, it means your expectations should shift. You don't have to accept web tools that hold your data hostage behind an upload screen, or applications that buckle and crash when you give them real work to do.
The overarching theme here is that the era of the browser being just a passive viewer is entirely behind us.
Yeah.
It is a remarkably sophisticated computing engine capable of orchestrating highly complex local system operations.
And as we wrap up, there is one final note in Aaron Rose's article that really pushes that idea to its logical extreme.
Oh, the web workers part.
Yes. At the very end, he teases this topic of web workers. Because he points out that even with the incredible efficiency of Streams keeping the event loop clear, some mathematical transformations are just so CPU intensive that they deserve their own completely independent thread.
Entirely separate from the main browser execution context.
Exactly. And it leaves you with this really provocative thought. If modern web browsers can now negotiate direct read and write access to your local file system,
Right.
if they can manage persistent local databases, if they can stream and process massive data sets without overwhelming the memory heap, and if they can use web workers to spin up independent, multi-threaded background processing environments.
Yeah. Where does it end?
At what point does the web browser stop being an application that you launch and simply become the operating system itself?
That's a huge question to think about.
It really is. So next time you are sitting there staring at a frozen web tab, just remember, the browser isn't weak. It's just waiting for the right instructions to show you how powerful it really is.